Okay, so now I'm going to go to Holt-Winters.
Hello, and thank you for tuning in to this video discussing Holt-Winters forecasting method, also known as exponential smoothing with trend and seasonality. And this name already reveals why this forecasting technique can be useful when data exhibits trend and/or seasonality. And that's exactly the case in the data set we're looking at here. You see, I've already graphed it for you. Here we have a little over 2 years worth of data. In this case, we're having weekly data. And if you look at this graph right here, you notice a recurring pattern that indicates seasonality over the course of about 2 years. And you also see a little bit of a trend, a little bit of a positive trend to be specific. So in this instance, we are well advised to use Holt-Winters forecasting method because it will adequately capture not only the level of demand, but also the seasonal variation as well as the trend over time. In this video, I want to show you how to actually implement this forecasting technique. Now, I'll be honest with you, it's a little bit more involving in terms of requiring us to go through a series of steps to actually calculate forecasts. But again, we're doing this here because it's very powerful and actually widely used in practice. So we're going to start out by taking a look at how we actually develop the forecast. So in Holt-Winters, what we basically do is we break down an actual demand observation into 3 components. And those 3 components are the base level, the trend component, and the seasonal factor. As we implement Holt-Winters, we first need to decompose actual demand observation, and that's our point of sales data. And ultimately, when we develop forecasts, we will recompose the demand expectation by summing up all 3 elements. That is the base level, trend, and seasonal component. It is called exponential smoothing with trend and seasonality because similar to the simple exponential smoothing method, we apply smoothing factors. The difference is here, as we break down demand into those 3 components, base level, trend, and seasonality, we will then apply a smoothing constant to each one of those components, which is why we have 3 smoothing factors, that is alpha, beta, and gamma. Let's go and actually implement this technique. First, we must start out by seeding the seasonal factors. The way we do this is we simply start out with the first period for which we have data, and we take the actual demand observation and subtract from it the average demand observation of the course of the first year. In our case, that is, of course, the first 52 weeks of data. So I take the average of the first 52 weeks, and I'll subtract that from the actual demand observation of the first period. Notice that I locked in the cell reference to the average of the first year worth of sales data. I'm doing that because I'm going to drag down this formula throughout the first year of data. So right now you see that the point of sale for week 1, for example, was 591. That is 147 units less than the average demand level over the course of the first year. So this is my seeding seasonal factor for week 1. And again, as I've just said, I'm going to drag down this formula for the remainder of year 1. Now notice, of course, that all the seasonal factors clearly sum up to 0, because again, I'm subtracting the average demand observation over the course of the first year from each individual demand observation. So this is my seeding estimate for the respective seasonal factors associated with every week. Now in the next step, we'll go to the last period of the first year worth of data, which is week 52. Now we're going to continue to seed our elements. We have already seeded seasonal factors. Now let's seed the baseline. This is actually quite simple. All I do is I take the actual point of sale observation, 768 in this case, and subtract from it the associated seasonal factor of 29.87. So I get a seeding estimate for the base level for week 52 of 738.13 units. And last but not least, we're going to see the trend factor. Now this is the easiest thing ever. We're simply going to seed it with 0. That's a common practice. So now we have beginning estimates for base levels, trend, and seasonality. And now what we're going to do for the remainder of the data set, we will continue to refine our estimate of base levels, trend, and seasonality. And the way we do this, remember it's called an exponentially weighted moving average. For each of these components, we're going to weight different ways of estimating these components. Let's start out by taking a look at the base level. For the base level, the smoothing constant is alpha. So I'll type here alpha. And now the first way of estimating the base level is to simply take the actual demand observation of the current period and subtract from it the most recent relevant seasonal factor element estimate. Now this sounds very complicated, but all it really means is that I subtract from the current actual demand observation the seasonal factor estimate from the year ago period. So since I'm in week 1 of year 2, then the year ago period that corresponds would be week 1 of year 1, which of course is period 1 in our case. And the associated seasonal factor was negative 147.13. This is one way again of estimating the current base level. Now I'll come up with another way of doing the same thing, and of course I'll again apply the weighting factor 1 minus alpha in this case, and the alternative way of estimating the current period base level would be simply take the prior period base level of 738.13 and add to that the prior period trend component, which was 0 in this case. Again, what I'm doing is I'm finding two different ways of estimating the current period base level, and I come up with a weighted average with alpha being the weighting factor. So right now, our base level would then be 767.93. Now, a similar thing for the trend component. And for trends, our weighting factor is beta. Beta times, and again, I'll find two different ways of estimating the trend. The first way would simply be to take the current period base level and subtract from it the prior period base level estimate. So the difference, or the increase or decrease in base levels, would be an indication of trends. Now, the alternative way of estimating a trend component would be weighted by 1 minus beta, and the alternative way of estimating the trend component would simply be to assume that the current period of trend is equal to the prior period trend, which in our case happened to be 0. So now we get a trend estimate of 2.98 for week 1 of year 2, or period 53. Now last but not least, we'll do the same thing for the seasonal factor. And here we'll use gamma as a weighting factor, or also called a smoothing constant. Now again, we find two different ways of estimating the seasonal factor. The first way would be to take the associated actual POS observations of 740 units in this case and subtract from it the associated base level estimate. In other words, I could argue that the difference between POS and base level, which is really what's accounted for by seasonality. And again, I add to that 1 minus gamma times again the alternative way of estimating the current period seasonal factor. And that would be simply to assume that seasonality is really the same value that it was in the year ago period. So that takes us back to week 1 of year 1. So again, I come up with a weighted average for seasonality. So now you see what I did was I broke down the POS observation into 3 distinct components, that is base levels, trend, and seasonal factors. These are estimates, and I come up with 2 different ways of estimating each one of these components and weight them by applying the respective weighting factors. Now the good news is that now that I have set up these formulas, I can simply copy them down throughout the remainder of the data set. So that takes us all the way through to period 109, or week 5 of year 3. And now I can finally come up with my actual forecast. So everything that I've done up until this point was really just to obtain these numbers right here. I need base level estimates, trend estimates, and I need a series of seasonal factors. Now my objective is to develop forecasts for the remainder of year 3. So I want to come up with forecasts for week 6 of year 3, or period 110, all the way through the end of year 3, meaning all the way through week 52 of year 3, which is period 156 in our data set. So let me show you how I'm going to do that. I'm going to start out by simply coming up with a 1-week forecast. So I am in week 5 of year 3, and I want to know or estimate what demand might be in week 6. The way I do this, I simply use the most recent base level estimate. And I'm going to lock in the cell reference because I'm going to rely on the most recent base level estimate for all subsequent forecasts. And I add to this most recent trend component estimate, which happened to be 9.7 in our case. Again, I'm going to lock in the cell reference because this is my most recent estimate for the trend component. So this is what I'm going to use for all subsequent forecasts. To that, I'm going to multiply this week's period minus last week's period, and I'm going to lock that. Since I'm in week 6 of year 3, the most recent relevant seasonal factor estimate will be that of week 6 of year 2. So I'll have to go back to the year ago period. So let me scroll up a little bit to find week 6 of year 2. So you see the associated seasonal factor estimate was negative 148.5. So now you see this is my forecast for week 6 in year 3. So this is an actual out of sample forecast. Now I can drag down this formula. This concludes the basic demonstration and introduction of Holt-Winters. Again, it is important to understand the conceptual underpinnings and the ability and the capability of Holt-Winters in terms of capturing trend and seasonality. That's a unique feature of Holt-Winters. It makes it very powerful with practice, of course. And again, we have to practice a little bit the implementation of this method. Again, I understand that there are a few steps involved, but please try to do these and replicate what I just did. Again, if you have any questions, feel free to contact me. Thank you for watching.
So that is video 1 on Holt-Winters. It's the same woman, she just gets a little more involved. With the Holt-Winters. So let's go to part 2.
I saved hundreds with Liberty Mutual. I'm good.
Hello, and welcome back for another discussion and demonstration of the implementation of Holt-Winters forecasting method. In this video, I not only want to show you again how to implement this forecasting technique, but I also want to talk a little bit more about forecast accuracy assessment. Now we're looking at a different data set here. This data set actually spans 12 years worth of data from 2000 all the way through to 2012. And if we plot this data, which remember we should always do first, we're going to get this line right here. You see, of course, it's easy to make out a positive trend. And also there's a little bit of a squiggly up and down, which is in part actually might be attributable to seasonality, which is why, of course, this data lends itself well to the implementation of Holt-Winters forecasting technique. Now let's jump right in and do just that. Let's get rid of this graph, and what I'm revealing underneath are the formulas that we can use to implement these calculations for Holt-Winters forecasting technique. And we can simply read those formulas to guide what we need to calculate. Before we get to do that, though, remember the first thing we need to do is to seed the seasonal components. And the way we do this is we take the actual demand observation and subtract from it the average demand observation, of course, of the first year, which of course is the first 4 quarters in this case. So I get a seasonal factor component, a seed of negative 690 for the first quarter, and I simply copy this down through the remainder of the first year. And now I continue with the seeding exercise, turning my attention to the base level, and I seed this as the actual demand observation minus the associated seasonal factor estimate. Next, we see the trend component, which remember we simply start out with a 0. So now that we have done this, we can go ahead and calculate weighted moving average estimates for the base level, trend, and seasonal components. And remember, to do that, we first need to define our weighting factors alpha, beta, and gamma. I'll just pick some arbitrary values here for now, 0.25, 0.15, and 0.25. So with that being done, let me go ahead and start out by taking a look at the base level, which is alpha times the first way of estimating the base level is to take the actual demand observation in the current period y sub t and subtract from it the most recent relevant seasonal factor estimate s sub t minus p, where we call p stands for periodicity. That is 4 in this case because there are 4 quarters per year. So s sub t minus p, since we're in period 5, would be s sub 5 minus 4, which is period 1, or the seasonality factor of winter of 2000. So that's what we're subtracting here, plus 1 minus alpha. Now the other way of estimating the current period base level component would be to take the prior period base level estimate and add it to the prior period trend component. So that gives me an estimate of about 10,340 in terms of the weighted average base estimate for period 5. Now we'll implement similar calculations for the trend component, that is beta times. Now one way of estimating the trend would be to look at the increase or decrease of the base levels. In this case, we're looking at an increase, of course. So E sub t minus E sub t minus 1. That's one way of estimating the trend. The other way, of course, would simply to apply weighted factor of 1 minus beta times the prior period trend estimate, T sub t minus 1. Finally, we're getting to the seasonal factor. So here the weighted factor will be gamma, and one way of estimating the seasonal factor would be to take the difference between current period actual demand and the current period base level estimate, y sub t minus E sub t, or of course 1 minus gamma times the most recent relevant seasonal factor estimate, which again is C sub t minus p. So now I've started or implemented the weighted average calculations for base level, trend, and seasonality. I can simply go ahead and copy these calculations all the way down throughout the remainder of the data set. With that done, I can now proceed to calculate my auto sample forecast. In other words, I can calculate my forecast for the year 2013, which would then be equal to, as we see to the right, the formula, the most recent base level estimate E sub t plus the most recent trend component T sub t. And now, of course, I want to make sure I'll add this the appropriate number of times, which will be the difference between the current period and the most recent period with an actual demand observation, which is period 52. And finally, I will add the most recent relevant seasonal factor estimate. And if I'm in winter of 2013, that will be that one from winter of 2012. So that gives me an auto sample forecast of 14,856 for winter 2013. And if I copy this down, you'll see I have my auto sample forecast for the remainder of the year as well. So with that being done, now let's take a look at forecast accuracy assessment. And that's something that we haven't talked about before. And it ties into those values for alpha, beta, and gamma, which recall I chose arbitrarily. Now, of course, I do not want to assess the quality of my forecast and the validity of these chosen values for alpha, beta, and gamma. Now in this case, I have a very long time period, and that affords me a certain luxury. In fact, what I can do is I can implement these forecasts the way we just implemented them, and I can pretend I didn't have the associated demand observation. In other words, what I'm trying to say is let me skip the first 2 years and start in the year of 2002. Now the reason I'm starting here, by the way, I now have for the entire preceding year estimates for the seasonal factors. And I have, of course, weighted estimates for the most recent base level and trend as well. So if I was in the winter of 2002, then my forecast would have been the most recent base level estimate, which was that of fall of 2001, and I would have added to it the most recent trend component, and I would have added to it the most relevant seasonal factor, which would have been that of winter of 2001. So you see, I would have at that point in time calculated an out-of-sample forecast of 9,938. And of course, I can do the same for the remainder of my data set. And now this allows me to evaluate just how accurate would these forecasts have been. And to do that, of course, all I need to do is take the actual demand observation and subtract from that the associated forecast that gives me the forecast error. And I'll also calculate the absolute value thereof. So now this will give me a means to assess just how good these forecasts actually are. So I'm going to go ahead and calculate the mean absolute deviation, which you recall is simply the average of all the absolute forecast errors. And I'll calculate the mean error, which is the average of all the nominal forecast errors. So now with that being said, I can figure out with this change if I change the values of alpha, beta, and gamma. So for example, what happens if I change alpha to, let's say, 4? Now you can see here my mean error of uncertainty goes down quite a bit, although my mean absolute deviation goes up. What I can do, of course, is I can use the computing power of Excel to find the values of alpha, beta, and gamma that will actually minimize forecast errors. So what I will do is I will use Excel Solver, and I will tell Solver to minimize my mean absolute deviation by changing the values of alpha, beta, and gamma. That's what you can see in cells B1 through B3, subject to a number of constraints. Remember, of course, that these weighting factors have to be between 0 and 1. However, prior research has shown that for all intensive purposes, you usually want values of alpha between 0.02 and 0.51. Likewise, beta should be between about 0.005 and 0.176. And finally, gamma should be between 0.05 and 0.5. So I've implemented those values as constraints down here, as you can see. And now if I click on Solve, what Excel will do is it will find those specific values of alpha, beta, and gamma that will truly minimize forecast errors or maximize forecast accuracy. In this case, in terms of the mean absolute deviation. Now the one caveat I want to highlight, though, in terms of using this optimization procedure to find the best possible values for alpha, beta, and gamma in terms of minimizing forecast errors, is that we need a fairly significant amount of data to do so. And again, the reason being, I really wanted these 2 years worth of data, and that's because to calculate these forecasts, I would need a most recent relevant seasonal forecast estimate that is weighted, and that's why I really need these 2 years. In the first year, I have seasonal factor estimates, but those are not these weighted average estimates that I really want to use, that are probably better ways of truly gauging the degree of seasonality. So that's why I need to start with a data point beyond the second year. And then, of course, I want to have a meaningful amount of data to assess forecast errors over a long period of time, so I can really reliably estimate mean absolute deviation and mean errors and find ways of minimizing those. One other issue, of course, is that what do I want to minimize? The mean error or the mean absolute deviation? I could, of course, also try to find the values of alpha, beta, and gamma that bring the mean error as close as possible to 0. And in this case, of course, the resulting values of alpha, beta, and gamma might also be different than if I chose to minimize the mean absolute deviation the way I just did it here. This concludes this discussion of the Holt-Winters method. Please watch my third video on Holt-Winters, where we talk about finding the reorder point.
Okay.
From idea to submission, empower students to do their.
So that was Holt-Winters. She's got one more part here where she does some confidence intervals and some other things that are kind of interesting. That's another 12 minutes. Remember, this is way more than you'll need to know for ISM test. For the ISM test, all you need to know is Holt-Winters is an extension of exponential smoothing.
Hello and welcome to another discussion of Holt-Winters forecasting method. In the previous series of videos, I introduced you to Holt-Winters, which is a great forecasting technique when data exhibits trend and/or seasonality. So in the previous videos, I showed you how we can implement Holt-Winters forecasting method with at least 2 years worth of data. And recall that we need at least 2 years because the first year we use to seed the seasonal factors. And remember, the way we do this is we take an actual demand observation and subtract from it the average demand observation over the first year worth of data. So once we have seeded the seasonal factors, we then proceed to decompose actual demand into base level, trend, and seasonal components. And remember, the way we do that is we first seed the base level estimate in the last time period of the first year of observations. So in our case, we're looking here at December 2008. And we simply do that by taking the actual demand observation, so that would be 53,263, and subtracting from it the associated seasonal factor. Likewise, we see the trend component, typically using 0. And we have the seasonal factor, of course, calculated as I just mentioned. And then we use that information to continue and to use the second year worth of data to decompose actual demand observations into the 3 components based on trend and seasonal factor. Now recall, just to remind you again how we do that, is we use weighting components, alpha, beta, and gamma, respectively, to calculate weighted averages for these 3 components. So we're looking at the base level, for example, use weighting factor alpha, and then we basically apply that weighting factor to 2 different ways of estimating a base level. The first way is to take the actual demand observation of that period and subtract from it the seasonal factor that corresponds to this time period 1 year earlier. So in other words, we took a demand of 55,735 and subtracted from it the seasonal factor from January of 2009. $9,286 negative 9,286, that is. And then we added 1 minus alpha, that's the other weighting component, and that consists of the base level from the previous period augmented by the previous trend estimate. So you see, this is our weighted average estimate of the base level. Likewise, we implement similar approaches for trend and seasonal factor. For trend, we use beta as a weighting factor, and then we estimate trend again in one of 2 ways. First, we take the current base level estimate and subtract from that the previous base level estimate. Or of course, we weight by 1 minus beta, the prior period trend component. And finally, we did a similar thing for the seasonal factor. Here the weighting factor is gamma, and we weight gamma, the first estimate. We apply this weight to the first estimate of the seasonal factor, and that simply is taking the actual demand observation and subtracting from it the corresponding base level estimate. Or, of course, another way of estimating seasonality would be applying the weighting factor 1 minus gamma and using the prior year seasonal factor. So far, I'm not telling you anything new. This is what we've done previously. Now, what we did do in the prior video, if you recall, is we calculated in-sample forecast. And the way we calculated in-sample forecast is we added up base level, trend, and seasonal factors to come up with a forecast. And then we proceeded to calculate forecast errors and so forth. Now, I also showed you how you can then use this forecast and associated forecast error information to find the values of alpha, beta, and gamma that minimize forecast errors. Now, I'm not going to do this here. Now, remember, I told you one thing in those preceding videos, and that was there's a little bit of a problem with doing that. And that's because these forecasts here are hypothetical or theoretical forecasts, in the sense that they clearly incorporate current period demand observation information. So they are not really real. They're not true forecasts. And if we fit the values of alpha, beta, and gamma to these somewhat abstract forecasts, we actually run the risk of fitting alpha, beta, and gamma to something other than systematic forecasts and other than systematic forecast errors. So it's a little bit of an artificial exercise, if you will, that might cause us to fit alpha, beta, and gamma to random variability rather than to structured forecasts and associated forecast level. So in this video, I want to show you something else that we can do if we have more than 2 years worth of data. So I'll get rid of these in-sample forecasts, and as it turns out in this example here, we have more than 2 years worth of data, and I've color-coded those. In fact, we have a little more than 3 years worth of data. We have 2 years, as we just discussed, and then we have demand data continuing all the way through February of 2013. Now what I want to do now is show you how we can use this kind of data to actually do a better job implementing Holt-Winters forecasting method. And specifically, what we're going to do is we're going to calculate forecasts the way we do if we didn't have actual demand information. In other words, let's take a look at January 2011. So let's put ourselves back in time to December 2010 and ask ourselves, how would we implement or how would we forecast demand for January 2011 if we didn't actually have demand information for 2011? Well, of course, the answer is, well, the forecast would be equal to the most recent base level estimate plus the most recent trend estimate plus the most recent relevant seasonal factor estimate. In our case, negative 6,405. So this is a forecast that is truly an out-of-sample forecast in the sense that if I am in December 2010, this is my best way of predicting what future demand will be in the next month in January 2011. So this is a more meaningful forecast than those in sample forecasts that we have previously discussed. Now, of course, what I can do again is I can calculate forecast errors, so actual demand minus the forecast, and I will look at the absolute value of that as well. And remember, I need that to calculate certain forecast error statistics. So likewise, of course, I can now continue to break down actual demand observations into base level, trend, and seasonal factors. In other words, so let's say we roll into January 2011, and at that point we will be concerned with forecasting demand for February 2011. And of course, the way we should do that again is we should use the most recent base level estimate and the most recent trend level estimate and the most recent relevant seasonal factor estimate to forecast demand for 2011. In other words, what we're going to do is simply copy all this information through the remainder of our data set. Again, the key difference here is that these forecasts are generated using information from preceding periods only, not incorporating the actual demand observation of the current period. In other words, they are what forecasts would have been if we had generated them ahead of time. So accordingly, these forecast errors here are really more meaningful because these are probably the forecast errors we would have truly encountered had we had to forecast demand for January 2011 and onwards. Now, what I can do then, of course, is I can go ahead and calculate my forecast error statistics. So when we do that, we need to get the mean absolute deviation, of course, would be the average of all absolute forecast errors, in this case 3,354 roughly. Likewise, the mean error is going to be the average of all nominal factor errors. In this case, we're getting negative 928. We can also look at the mean absolute percentage error if you wanted to. I'm going to skip this one for now, but I will take a look at the standard deviation of forecast errors. So standard deviation of nominal forecast error gives me 3,874 roughly. Now what I can do then, of course, and I will show you that in a moment, I can find those values of alpha, beta, and gamma that would minimize forecast errors. Before we do that, though, I just want to do one more thing, and that is actually calculate, of course, true out-of-sample forecasts. So notice that I have to mandate up until and including February 2012, but that's the end of the line. So I can then calculate my out-of-sample forecast as the most recent base level estimate plus the most recent trend estimate plus the most recent relevant seasonal factor estimate, which would be that of March 2012. So you see I get 96,059. I'm going to copy this formula down, but remember one important thing. See, actually a few important things. First of all, we need to lock in the reference of the base level. We need to lock in the reference of the trend level as well. But in addition, we need to make sure we add the proper number of trend components. So that will be 2 times for April 2013 and 3 times for May 2013. So you see here with the given values of alpha, beta, and gamma, I would get forecast values of 96,059, 100,000, 101,425, and 99,213 for March, April, and May of 2013, respectively. Now let's go ahead and calculate the reorder point here for a normal distribution assumption and a 96% level. So I'll calculate the safety stock requirement here as a norms inverse of 96%, and I will simply multiply that by the standard deviation for forecast errors. So I get about 6,782. And that gives me a reorder point for March 2012. That is equal to the sum of the associated forecast and the safety stock we just calculated. So 102,841. Now let me copy these numbers and paste them as values to make sure they won't change. And now we'll do that. And now we'll do what I had mentioned earlier. We're going to ask Solver to find values of alpha, beta, and gamma that will minimize the standard deviation of forecast errors. Of course, subject to the usual constraints, that is, that of alpha, beta, and gamma should fall within pre-specified ranges. Now I click on Solve and see what I find is that alpha should be ideally about 0.24, beta about 0.176, which is its maximum value, and gamma 0.5, again reaching its maximum value. Once we do that, notice how, of course, the forecast changed. So again, I'm going to go ahead and copy those over here, and accordingly our safety stocks and reorder point will change as well. Notice now that the standard deviation of forecast errors has changed, as well as after optimization. We're going to be looking at norms inverse times the new standard deviation of forecast errors. And you see, of course, I need less safety stock because I've managed to reduce uncertainty by fitting alpha, beta, and gamma. And as a result, my reorder point will change as well. So that will be the sum of the associated forecast and the new lower safety stock. So this really is the best way probably of implementing Holt-Winters. The key idea being I will evaluate forecast errors only when I have enough data to actually develop forecasts using only prior period demand information, as opposed to including same period demand information. But that only works if you have at least 3 years worth of data. As always, if you have any questions about Holt-Winters, above and beyond what we have just discussed, feel free to reach out to me. And thank you for watching.
Okay, so that is Holt-Winters. We'll go into autoregression and moving averages next, but that'll be a different video.